Welcome to another Ultralight Airplane Structural Analysis video from the Ultralight Airplane Workshop. I'm Leon. Now in this video, we're not yet getting to the structural analysis. That'll be the next video. Now in this video, which is part 4 of the series, doing structural analysis on a truss style rib for an ultralight airplane. In this case, it's the UWS-4 Ultralight airplane that I'm designing. There's a whole bunch of videos here on the channel covering that. But in this case, it's a truss style rib. And you can kind of see it here, where you got beams top and bottom, and then you got the braces here. Now, I've previously done a series on structural analysis of a cantilever style rib. I'll put a link to that video up here in the upper left-hand corner. Now, in this video, part 4, I'm going to do a quick video on assembling this little structure. Now, this structure's sole purpose is to test this rib inside. So to test this rib, to give it more realistic loads, like we're in flight, I'm putting it into something very similar to what I'll do on the airplane, which is it'll have a skin on it and a spar. So the spar is composed of parts which will be very similar on the real airplane. I got 2 caps, I got a shear web, and I got some stiffeners here on the edges. I also have the same thickness of skin I'm going to be using here. This is 16 thousandths of an inch aluminum. And just as a reminder, if you haven't seen the previous videos on forming this nose rib, in fact, I'll put a link up here in the upper right-hand corner so you can see how this is formed. This is also 16 thousandths aluminum down here in the rib. Now I need to apply a load on this similar to the way it's going to be applied in the air. And I'm going to do it at the maximum load, plus some safety factor. So maximum load is 3.8 Gs. I've got the gross weight of the airplane at 560 pounds now. So you take that 560 pounds, multiply by 3.8, that'll be the maximum load on the wing. And then there's a 50% safety factor, so you multiply by 1.5. And that gives you the total load I want to test to. Now load along the wing is not consistent. If there's more load at the root than there is at the tips. So I have to take into account the distribution of the load on the wing. I have a spreadsheet set up to let me do that. And I figured out what the maximum load on a rib, a single rib, will be at the root. And so that's the worst case scenario. So I want to be able to put a load on this skin here just like it will be in flight, or at least a distributional load. Now I happen to know what the distribution of that load is in the chord-wise direction. I have a spreadsheet that's set up that has all that information. So I'm going to put load on here similar to the way it'll be at flight, 3.8 Gs, and that extra 50%. Now the way I'm going to do that load is I'm going to have these little tabs that I'm going to use super glue to glue down at each rivet location. So I know how much load each of these rivets is going to have. So the skin has a distributed load, but the load is transferred to the rib through the rivet. So I'm going to put that load fairly close to where each rivet is, the correct amount of load for each of these tabs. By the way, when we're in flight, that load is coming up this direction. There's not much load pushed on the bottom. There's a little bit. I'm going to ignore that for this test. I'm going to put all the load pulling up here. Now the majority of the load is up here near the nose, the front of the nose, and it tapers off as it goes back. In fact, if you concentrated all that load on the nose into one spot, it'll be 7.5 inches back here from the leading edge. Now I need to know all that information to make this. I have a video on making this. This is a whipple tree. This is what's used to distribute the load at each location. So this load up here at this location where I'm going to put the maximum load pulling up, this is going to be 7.5 inches back from the leading edge. And then by adjusting all the links on these arms, I can get the correct load at each of these rivet locations, which will be transferred down to the tabs with these metal wires. And so I'm going to have a hole at the top of each one of these tabs that a metal wire will go through. Now I've also got a rig set up. There's going to be a ram that's going to pull on this. There's also going to be a load cell, which will measure the load. And I've also fixed up a test stand that I can use. Now, I got to get this attached to the bottom edge of the test stand. And I quickly welded up these little gizmos. So these will attach to, whoops, sorry. These will attach to some holes that I have here in this spar, like this. And then I've got spots here, which is 7.5 inches back from the leading edge, that'll attach to the bottom of the test stand. And you can see the hole there. Now, I did not do a video on making the test stand. It took a long time. I didn't think it was that interesting, but you will get to see me use it in the next video. But in this video, we're just talking about assembling this. I had never done a video really on doing any metal working yet, and I thought, well, I'll go ahead and do a video of this. Now, keep in mind, in this video, I'm not using best practices. This is done fairly rapidly. I'm being a little bit careless drilling my holes. I'm not caring about scratches that go onto the skin. That's a bad thing. Scratches are a really bad thing. I'm not worried about nicks on the spar. I'm not really worried about if the rivets are very well seated. I did a fairly good job, but I do know there's a couple rivets that are not well seated. And I'm not using the best rivets. I'm using some off-the-shelf, kind of generic blind rivets. And I'm also not removing all my mistakes. For example, on the drill holes here on this top of the rib, I actually drilled a whole bunch of holes that are 1 inch off, so I left those holes in there. Now, I'm doing this partly just because I want to get going rapidly and get this done. The other reason I'm doing it is, what if we have a builder who's trying to duplicate what I'm doing and they don't use best practices? They leave scratches in there, which can lead to fatigue cracks after a while. And they leave nicks in the spar that can lead to fatigue cracks and failure in the future. Maybe they leave some extra holes in there that they shouldn't. Now, if I was working on the real airplane building it, I would have not used this piece of skin. I would have thrown it away. It's got the extra holes in it. It's got scratches in it. It's just subpar. Now, as we're going through the video, I'll be doing voiceover on the video, talking a little bit about what I'm doing. Keep in mind that I'm not showing every step that I'm doing. I'm doing a few jumps here and there just because I think it's either not important or I forgot to film it at the time. But I'm doing a lot of the steps that should be done. Well, let's get started. The first thing we're going to do is I'm replacing the old shear web that I used to have here on the spar, just because some of these holes were starting to get a little bit too big, because I had reused this rig several times doing the cantilever test. So we're going to make a new shear web and then proceed from there. For the shear web on the spar on this test fixture, I want the vertical edges to be stiffened. I'll add stiffeners to the real spar in between, about halfway in between ribs, so I might as well go ahead and do that here. I have a pen and box brake here that I'll use to bend those edges. You see that gray strip of metal that I have there on the edge of the brake that's clamped down? It's there to give me a guide to have about a 1/2 inch bend on the edge of the metal. Now, I ended up making it just a little bit too long. I wish it had been about 1/8 of an inch shorter, but it'll still work out okay. Before I can use that new shear web, I need to remove the old one. Now, I decided to go ahead and record this just to kind of give you an idea of one way to remove old rivets. And you can remove old rivets without too much trouble, without too much damage, at least once. One of the reasons I want to replace this shear web is that this old one that I have on here right now, this center line of rivets, that vertical line, I've replaced the ribs on here often enough. The middle line is where the rib attaches. I've replaced the ribs on here often enough that a few of the holes are starting to get slightly elongated. This wouldn't be quite as much of an issue on a thicker piece of aluminum, thicker sheet. This is only 16 thousandths. So if I happen to drill just a little bit too much into the rivet head and into the sheet, that's an issue. Now in this case, I'm only removing the rivets that are on the spar caps, so the line along the top and the line of rivets along the bottom. Now, the way you remove these rivets is you drill right into the center of the rivet head. And you drill just enough that you can get down to the surface of the metal underneath. You don't need to drill any more than that. And the reason is, if you're offset just a little bit to left, right, up, and down, you'll start drilling into the material itself instead of the rivet. So you want to drill just enough that that cap can come off. So I'm doing that for all these rivets along here. Now, that still leaves the mandrel and the body of the rivet inside the hole. If your rivet has been installed properly and it's a good rivet, that's going to be in there fairly tight. It's not going to want to turn. That's the issue I have with two of the rivets here. is they weren't in there very well, and the body actually turned as I was trying to drill the rivet. And of course, if the rivet's turning along with the drill, you're not going to be able to drill anything into it. So I have to hold the back side of it with some pliers in order to do that. But it also tells me the rivet wasn't installed very well. But to get rid of the shank when it's in there tight, I just use a center punch and punch them out. And they come out fairly easily. Now, if this was a driven rivet, a solid rivet, those grip much, much better, and it's much more difficult to knock out the body. But on a solid rivet, you still use a very similar technique. You drill into the center head, down very close to the metal. You don't necessarily have to go all the way to the underlying metal. You'd actually stick a piece of rod in the hole that you drilled, and you can twist it sideways and pop the head off. So you don't actually always have to go all the way down to the underlying metal. So it's pretty easy to remove old rivets, especially if you make a mistake. You damage the aluminum, you drill holes you're not supposed to. You can remove the old rivets and put a new piece on. Next it's time to install the shear web for the spar. What I need to do is drill the holes through the existing spar caps into the shear web. I'm going to use a piece of wood that's backing the shear web to hold it up against the spar cap. I'm going to keep it as flat as I can so the holes will be in the right spot. Then I use the existing holes in the spar cap to drill the holes through the aluminum shear web and into that wood. Once I have that done, I use clecos through those holes I just drilled to hold the shear web to the spar cap. Now I don't have to fill every hole. I can see that the spar cap is laying pretty flat along the shear web, so I'm just using every other hole. And then I basically repeat the process on the bottom spar cap. These clecos that I'm removing here are temporary fasteners, and we're going to be using these temporary fasteners a lot. One of the things that happens when you drill holes, especially if you don't have a really sharp bit, is you're going to get burrs around the edges of those holes, both on the front side and on the back side. Almost impossible to drill a hole without getting some burrs. Well, those burrs, when you put two pieces of metal together, will keep those pieces of metal from meeting flush, meeting flat. And when you go to rivet them then, with that space in between those two pieces of metal, that gives forces that are trying to shear those two pieces of metal, gives them a little bit lever so it can start working that rivet back and forth. And so you've got to get rid of those burrs. And so that's what I'm doing here. I have a countersink bit that I'm using by hand to just give a little twist on each one of these holes to get rid of the burrs. I do it on the front side and the back side. I do it for every single hole that I drill. Now, you don't know it at the moment, but I haven't drilled all the holes yet in this piece of aluminum, this shear web for the spar. I have to put it back on the caps, and then we're going to have to drill the holes for the nose rib, and then I got to take it all off again. So I'm going to use the clecos again to hold this shear web back onto the spar caps while we work on the nose rib holes. And so you can end up taking the clecos on and off many times as you drill more and more holes in a part. And that's why the clecos are really useful. They'll hold fairly well, not as tight as a rivet, but they'll hold fairly well and they're removable. So they come in very, very handy. Now I was going to drill the holes for the nose rib on here and then take it all apart and deburr the nose rib holes, but I decided not to. I'm just going to go ahead and pop rivet this on here now. I can reach these holes pretty easily to deburr them with the web attached to the spar caps. So I'm going to rivet this web to the spar caps, top and bottom. You can see here that I only used a cleco in every other hole. I could see that it was holding it pretty flat in between, so there's no need to use a cleco in every hole in this case. I'm using a hand riveter to put these rivets in. These are blind rivets, just kind of off-the-shelf generic ones. And every rivet that I'm putting in, I'm trying to make very sure that I'm pushing the head of the rivet flat up against that sheet so I get a close-in job. I don't want that head to be a little bit away from the sheet. I don't want it to be tilted, because then once again, shear forces between these two parts can start rocking that rivet back and forth and working it loose. So I'm going to do the same thing for the top spar and the bottom spar. It's time to start drilling the holes to attach the nose rib to the shear web. I've already got the top and bottom holes that'll attach the rib at the spar caps. that's left over from the previous use of the spar cap. So I'm just using a piece of wood here to line up the top and bottom hole and draw a line along where I'm going to put the new rivet holes. I'm also going to draw a line on the flange of the rib that's going to attach to the spar web, and I'll just do that by hand. That's pretty easy to do with a finger up against the edge and just drawing along. I made a drill guide to help me drill the holes that are 1 inch apart through the shear web and into the rib. I'm going to hold it in place using clecos in the holes that already exist in the spar caps. And again, I'm going to use a block of wood as a backing block as I drill the holes through the shear web. And this drill guide comes in really handy for drilling a line of 1 inch spaced holes in a nice straight line. And I'll be able to use this drilling guide in other places where I have 1 inch spacing of rivets. And as always, those holes we drilled need to be deburred. So I'll deburr the front and back of these holes. Now we're going to use that line that we drew on the flange of the rib. We're going to use that line on the rib to line up with the holes that we just drilled in the shear web. That lets us get that rib in the right spot, and then we can drill through the shear web holes and make holes in the rib in the correct location. So what I need to do is press that flange with the line up against the holes, and then I can look through the hole and line up that line. And then once I hold that rib in place, I can drill the holes and have them in the right spot. I have a piece of wood that I'm going to use as a backer board as I drill these holes. Then I'm just going to use the existing holes in the web, drill for those into the flange of the rib. And here you can see I'm using the backing board by hand because there really isn't enough room to stick a board as I have before in there. So once again, we have to remove all these clecos because we need to deburr the holes in the rib. Deburring the holes on the outside of the flange is easy. I can still use my countersink bit to do that. But the holes on the inside of the flange is a little harder. That flange is a leg of a U shape, and it's only about a 1/2 inch by 1/2 inch. So there isn't room to get a countersink in there to deburr the back side of those holes. So I have a different little tool I use for that. It's a scraper. So I can stick that scraper through the hole, angle it, and then I can scrape the back side of the hole to remove the burrs. Now we have to cleco the rib back to this web spar so we can start figuring out how we're going to drill the holes from the skin into the rib. All right. Well, now it's time to start working on the nose skin. So the first thing I'm going to do is I'm going to draw where the line of rivets are going to be on the wing skin. The rivet spacing on the wing skin, at least on the top, is 2 inches apart, except for the very first spacing. So the first one that's in the spar cap to the first one that's in the nose rib. That's actually 1 inch. And then everyone after that going forward is 2 inches. Well, I made a mistake here. I made that first gap 2 inches instead of 1 inch, which means I drilled all the holes in between where they're supposed to be except for the spar cap rib. I'll go ahead and correct that later on. I'm not going to bother showing it. I'm just going to show the mistakes that I drilled here, but essentially it's the same thing. Now, I did leave these extra holes in there just because they won't really make any difference in the end on doing this truss rib testing that I'm going to do. But in building a real airplane, I would not leave it. I would have scrapped the piece and started over. For the moment, I'm just drilling the holes that go in the top of the skin. The holes in the bottom are a little bit later. And of course, once I've drilled some holes, I need to go and deburr them. And again, I'm using this countersink bit by hand to do it. Well, now it's time to drill holes in the rib flange, at least the top rib flange. Now I'm going to do that by holding one finger along the edge of the rib and then keeping the marker the right distance from that and just marking right down the center of the rib. And again, I'm going to look through holes in the skin down to this line to line it up. So I need to hold the rib skin fixed on the spar, and I'll do that by putting a center cleco in here on the spar, and then for now just some temporary clamps along the edges. On a big skin, I would probably just go ahead and drill and cleco all the holes along the spar first before doing the rib. And then it's just a matter of lining up the skin hole with that line in the rib, drilling a hole and putting in a cleco and just moving forward. Now you can't see it. I have a hand underneath the skin holding the rib, moving it back and forth to get it in the right place. Just to get it lined up so I can see it through the hole. Well, now that I'm fairly confident I have that skin where I want it to be, I'm going to go ahead and drill the spar holes. And I'm going to use the existing holes to drill up through the spar and into the skin. Now I have a handy little tool here that lets me do that, because there really isn't enough to get the drill in there to do that. So I have this much smaller chuck that's an attachment for a drill that's a 9-degree angle and lets you get into tight spaces. So that's what I'm using here. It's very handy. And before I forget, I deburred those holes I just drilled in the top of the rib flange. And now comes the hand crafting part. And this is forming the skin to the shape of the nose rib. Now the skin is a little bit too stiff to bend around the shape of the nose rib that we have. There's kind of a sharp radius there. And you would have to use a massive amount of force to try to hold it in shape. And it really won't do a very good job. There aren't enough rivets to really hold it in shape, and there's a lot of spacing between ribs. So we really need to hand form this skin a little bit to conform to that nose rib shape. Now the method I'm going to use here is fairly easy if your skin is not too wide. Now this is only 12 inches, so I can actually use the method I'm going to show here and get away with it. Now if this sheet was 2 feet wide, 3 feet wide, 4 feet wide, even much wider, this little hand method I'm using here, it's much more difficult. I'm not going to say you can't do it, but you really need more complicated forms to get it to work well. Now I've already drawn lines on this sheet where the tightest radius is going around the nose. I'm going to set this form so it's perpendicular to the long side of the sheet. That way I have a straight bend. And then I'm just going to bend it over by hand. I'm going to sneak up on this a little bit at a time. I don't want to try to go right to the exact shape in the very first bend because I'll get it wrong. I could go too far. Going too far is bad. Trying to unbend something is terrible. I'll do maybe 70% of the bend, and then maybe another 20%, and then a 10% maybe. Something like that. Try to sneak up on it. Now once I've done the first bend, I take it over to the nose rib and I set it on there and try to see how much force it takes now to get it to conform to the shape of the rib. If it still takes a lot of force, I know I need to go a little bit farther. If it just fits right up there nicely with only just maybe a little bit force, then I got the right answer. But I don't have the right answer yet. And I realized that down in the tightest radius, I need to bend it even more. So I need a smaller diameter form. So I get a smaller one. And again, I have the marks on the sheet to keep that form perpendicular. So I do a little bit more bending. I take it over to my rib and I fit it up there again and take a look. And I can see that it still takes a little bit too much force to get that very tightest radius the way I want. So I go back and do one last little bend. Once I do that last bend, take it back over the rib, take a look. It takes almost no force at all to get it to move up against that rib, so I'm pretty happy with that. We'll go with what we got. Well, the rivet holes for the top of the rib are done. Now let's work to the bottom of the rib. Now I've turned the rib upside down here to make it a little bit easier to work on. My first objective is to figure out where that first rivet hole is going to be in the bottom spar cap. I want to get the skin tight around the nose and pushed in tight, and then I'll figure out where that last rivet goes there in the spar cap, and I'll mark that. Now I'll use that to figure out where the rest of the rivet holes go. The center line for these rivets on the bottom rib, the bottom skin, may be drawn. And then starting at that back rivet that goes in the bottom spar, the rivets are 3-inch spacing going toward the nose. So I'll mark the locations for those rivet holes. So you've basically seen all the steps I'll do to finish this off. I'll drill holes in this bottom skin, deburr the holes, draw the rivet center line on the rib, then I'll put the skin back on the rib. I'll drill through the holes in the bottom skin into the rib with that line that's on the rib lined up so I can see through there. I'll put clecos into the bottom skin, into the rib to hold that in place. And of course, deburring the holes. Then I'll drill holes through that bottom spar into the bottom skin. And then I'll deburr all those holes. And then for the finale, we get to start pulling out all these clecos and sticking in rivets. Well, there you have it. It's all assembled and it's ready to be put on the test stand and attach the Whipple tree and start doing some tests. So that will be the next video. So I think I'll go ahead and show assembling all this, putting it on the test stand, adding the Whipple tree, putting on the load cell, the ram, and then we will do the test and we'll show failures as they occur and we'll figure out how much this can handle before it fails. My goal is up around, if I remember correctly, 138 pounds for this rib. And as I said before, that's at 3.8 Gs plus an extra 50% safety factor. Well guys, that's it. Thanks for watching. Until next time.